We now look at damped oscillations, but we'll also go over it very quickly. So if you have a spring and we attach a mass to it and we pull it, then it's going to oscillate for a long time. But if you dip it in a fluid, let's say water, then the resistance of the water will cause it to slow down and stop very quickly. Or if you have a pendulum and it's there is some kind of air resistance, then it will stop very quickly. So such oscillations are called damped oscillations, in which the damping, there's some kind of friction that slows down the oscillations, and instead of the thing keep going like this, it sort of dampens out. So that's the time and the amplitude. So it damps out and stops very quickly. So systems need to be damped. For example, if we have a big building, steel structure, and due to an earthquake or due to the wind it starts oscillating, then if there's no damping, it will just continue oscillating for an extremely long time. So we do need damping in buildings and also in bridges. We don't want the bridge to keep on vibrating for a long time. We want there to be damping, and we have a damping coefficient, so we need to have something to cause it to dampen, especially for space structures in outer space, where there is nothing to prevent the damping. The thing would continue to vibrate if a vibration was set up somehow, and so they need to have ways to dampen it out. Here it would ultimately be damped out because it's touching the ground. Lastly, we will look at forced oscillations. And resonances. So a forced oscillation is one in which the oscillation is maintained by a periodic force. So let's suppose that we have like a pendulum, but it's a swing, and you have a child sitting on the swing. Then you pull the child and you let it go, and it will start swinging, but it very quickly will stop, and that's because there's a lot of friction. So if you want to keep the swing going, standing here, you would push every time the swing comes here. You push it and it will go and come back, and then when it's back here, then you push again, and then it goes and comes back, and then you push again. You don't push while it's coming towards you. So the push is at a certain time when it's back here. So it becomes a forced oscillation because you're maintaining the oscillation by applying a force. Now, the push that you're giving has a certain frequency, and the pendulum also has a certain frequency. So if the two frequencies match, then every time it's here, you apply a push, and then it's back here, and you apply a push. So in that case, if the friction is low, the amplitude will keep on increasing, and that is how we increase the amplitude of that's how we increase the amplitude of a swing. So we apply a periodic force that matches the period of the swing. Now, if this is done for anything else, for example, you have a glass and you apply, and we have some kind of a music, some kind of a sound coming from here, and it has a certain frequency, well, the glass would have its own natural frequency of vibration, which you can see by taking a spoon and tapping it, and you will hear a ting sound, and that is the natural frequency of the cup. So if you have a sound which has the same frequency, then every time the sound wave hits it, it will create a periodic force and a forced oscillation. It will start vibrating, and because it's glass, it can't vibrate too much and it can break off and shatter. The same thing can happen in bridges. So if you have a bridge and people are marching over it, and everyone puts the left foot down, then the right foot down, then the left foot, then the right foot, so there's a periodic force. If the period of that force or the frequency matches the natural frequency or the natural period of the bridge, then the bridge will start oscillating. It'll start going up and down, and it could ultimately fail. So this phenomena in which the frequency of the applied force matches the frequency of the object, then the amplitude keeps on increasing. This is called a resonance. So when resonance takes place, the amplitude of vibration increases, like it would here if you apply the force at the right time, or here if the frequencies match, or here. So in a resonance, they match. The amplitude of vibration increases and the object can break. In electronics, we have the same thing. So if you have a radio set and it has a, let's say, an antenna, and we have a radio station which is transmitting a certain frequency, then that frequency goes in here and it causes the electrons to vibrate with the same frequency, and inside it we have a tuning circuit, and if the frequency of the tuning circuit matches the frequency of what's coming in, then we have resonance, and the amplitude of those vibrations increase so much that we can put it into another amplifier and get some sound out of it. And that's how we catch the radio station, that our tuning circuit matches the frequency of the incoming waves, and then resonance takes place and the amplitude increases enough that it can be further amplified to produce sound.